Hello and welcome to Toddcast number 26. I'm always interested when I check the list the I guess recording to see what they typed in, but that would be a Toddcast. My effort to be funny. Anyway, this just picks up kind of where last one left off with thermo. Going to have our thermo review. This, however, this group of thermo information is a little more pertinent to what we're doing in OChem. So whereas the previous one, Hess's law, very much GChem oriented, not necessarily not important, but like the delta G equation, we use it in OChem, but the next stuff we actually pay a little more attention to. We worry more conceptually, and this will be a more conceptual way of doing the math. So bonds broken minus bonds formed, and a look at actually just how the molecules fall into place. So I want to start with a reaction that's known as homolytic cleavage. Homolytic means it gets cut. So a lytic process is one where this electron, I'm sorry, let me go back a bit. This electron goes there, it's single-headed. This electron goes there, single-headed represents one electron. And this free radical and this free radical exist. Homolytic meaning they each get one electron. So we talked about homolytic at the very, very early onset of the class. Now we're going to do a little more detail in terms of the energetics, the bookkeeping. So again, these are all bond association energies in an unstabilized environment, meaning it's not like it's a charged species being stabilized by water, which affects how well it breaks. This is strictly breaking into free radicals with either a aprotic non-solvating solvent or a gas phase or whatever medium they want to look at, but basically just the straight bond energy without any other factors. So table reads as follows: CH3, a methyl group connected to an H, 105. CH3 carbon-carbon bond, so CH3 connected to another CH3, 90, to an ethyl group, 89. So hopefully you can read across that way. Notice the anomalies when it's bonded to an sp2 aromatic carbon or sp2 in a benzene ring. Energetics goes up, but outside of that, it's kind of the same for most of them. Okay, so the extra little area down here, this little box that kicked in, is just how alkyl chlorides, how stable they are. So a really common reaction is something called halogenation, or in this case, chlorination. So I'm starting with a very simple molecule, methane. So methyl group bond to an H, so methyl and H intersect, so that's a 105. ClCl I can read here in terms of, oh, nope, I can't, but I can read methyl Cl. So that's an 85. So 105, 85. HCl is not listed in the table, Cl is not listed, so I'm gonna have to get them from outside resources. But 105 there and 85 there. And then if you happen to know, this is 57, same units, kcals per mole, and 103. Energies, I'm going to use some tables in terms of kcals per mole, some kilojoules per mole. It's a 4.18 difference, so whatever the kcal number is, multiply it by 4.18, and that's a kilojoule number. So it really doesn't matter as long as you're paying attention to relative numbers. But although joule is a standard unit for energetics. Okay, so I want to look at this a little more carefully. So it ends up, this energy is the energy to invest to break the bonds. So I must put 105 in to break this bond and 57 to break this bond. So I have to invest 162. But according to this, it releases 85 when this bond forms, and 103, meaning 85 and 103 is 188. So I'm going to invest a total of 162, but I'm going to get an amount of 188 coming out. So overall, I'm getting more energy out than I put in. So overall, it's energy releasing, meaning it's exothermic. So we can think of the bonds being broken early on. So these two numbers come into play here, although there's other factors like rehybridization. In the case of a solvent that does support it, solvation. So it isn't purely bond breaking, but that's the major part of it, why it goes up. You invest the energy to break the bonds. So we consider it endothermic because energy has to go in to break a bond, but you end up getting energy when you form a bond. So we say everything in chemistry is alphabetical. So we mentioned it's products minus reactants, and we deal anything with delta H, delta G, delta S. Here, it's broken minus formed. So broken is the energy we must put in, so that's a positive number, minus the energy released when the bonds form. So broken minus formed. So delta H for reaction is the energy of the bonds broken, in this case 105 and 57, so 162, and minus the energy of the bonds formed, 85 and 103 for 188 total. So if you did the math on this, 162 minus 188 give you around 26 kcals released. Okay, notice that the number we put in, small number in, so small investment to break, large return when it forms. So if you get more out than you put in, net loss, hence it's an exothermic or heat releasing energy, heat releasing reaction that gives you the energy. Okay, so if in an exothermic reaction, bonds that are formed are stronger than bonds that are broken. Just something to keep in mind. If you break stronger to form weaker, it's going to be endothermic, exact opposite. Okay, so again, the math here, 105 and 87 in, minus 85 minus 103, so minus 188 out, so 162 minus 188, there's the 26. Okay, so the math is doing fine. Want to bring up that ATP, ADP. So we mentioned it in a question from standardized test in the last podcast. So this one, just want to talk about what actually happens in this. So I mentioned the fact that biochemists will often say that you get energy by breaking the ATP bond. And it's a misnomer. What actually happens is you get energy because you break two bonds and form two better bonds. So do want to point out that this plus 30 kilojoules means delta H is minus 30, meaning this is like a product. This is the release of the energy. So this is written in a weird sort of way. So it's not saying delta H equals positive 30. It's saying you get ADP, inorganic phosphate, plus 30 kilojoules per mole, kind of like we dealt with in one of those previous questions. So here's the end of ATP. I didn't draw the rest of it, but here's the second and third phosphates. And when it breaks, here's just the second phosphate of ADP. So again, the first phosphate and the rest of the molecule, first phosphate and the rest of the molecule are not shown. So keeping track of things, we have PO, so that bond must be breaking at OP. And then here, H and OH, so probably that bond, but reality, it doesn't really matter that much. But we break this one, it's probably because it's easier for water to attack the terminal phosphate and break that bond. So we break that bond and break this one. And I could have picked either side, but I picked an OP and an OH. And we form now this new OH and this new OP. So the bond is broken are OP and OH. Bonds formed are also OP and OH. So at face value, you would say bonds broken exactly equal the bonds formed. So if they're the same, then same minus same should be 0. No change in energy, K equilibrium equal to 1. But we know from our experience in bio that we use ATP to store energy, and when we hydrolyze it, we get that energy back. In fact, it's 30 kilojoules per mole, roughly 7-ish in terms of kcals per mole, if you're keeping both units in mind. So I need to look a little more carefully at what's going on here. It ends up that it's not 0, I end up releasing energy, which means either one of these bonds is easier to break, weaker than expected, or one of these bonds is stronger than expected. Well, water is pretty much water. It's a good, strong bond. And then this OH here, or OP, excuse me, and this OH, they're not, I mean, there's nothing special, but where it does kick in, you have a negative O here and two negatives here, which means these negatives repel one another, causes this bond to stretch a little bit, elongate. Longer bonds are weaker bonds, so it ends up this bond here, this phosphate, is abnormally weak, a little bit weaker than expected. So put it in red. So if I have a weaker bond that I'm breaking, I don't have to put as much energy in. Therefore, I put less in, get more out. So smaller number minus larger number. Net result is a negative number, meaning you release energy. So this is an energy releasing or exothermic reaction. So delta H should be negative 30 kilojoules per mole, but I just wrote it as 30 kilojoules per mole as a product of the reaction. It is what's released. Okay, so let's apply it to an OChem reaction. I am going to make note, 2 molecules going to 2 molecules, a ring system that hasn't changed much with resonance and overlap, and an individual molecule. So I'm going to say that delta S be negligible, just point of interest. So our delta H and delta G will be really close. But this question focusing just on delta H. Products minus reactants. So let's figure out if they have that. Like, nope, this is bond energy. So broken minus formed. Only two options, broken minus formed or products minus reactants. This one, we're dealing with bond energies. And that's going to be what we focus on in OChem, bond energies. So our new bond is here, carbon to nitrogen. So carbon to oxygen must have been broken. So CO bond is broken. And then this only has one H, so an NH bond was broken. In exchange, an OH bond was formed and an NC bond was formed. So keeping track of everything. The bonds broken are CO right here. Actually, let me draw that for real. Just an arrow, that bond's broken, and an NH, that bond there. The ones that are formed would be an N to C and an OH. Okay, so now I just have to look at the table. The table, they give me an sp2 carbon to oxygen bond. So they don't specify it as sp2. So I'm going to assume that's sp2. And that's the problem with this. The numbers we put in are not always perfect. So without knowing enough details, but I'm going to just go with it. NH bond, again, I'm assuming that's sp3n, although in this case, I don't know, but seems reasonable. The CN bond listed as 305. That seems reasonable. And then water. So an OH bond is just generically listed as 467. But again, it didn't specify. So it could be from alcohol, could be from water, could be from a couple different things. So the table method is only as good as how close the bond I'm looking at in the reactant or the product is to the generic bond listed in the table. So bonds broken minus bonds formed. So these two numbers combine to make 749. Hopefully it seems there's 749. And then these combine to make 772. So broken minus formed. So for this one, plugging in, I'm going to have these do this. So 749 minus 772. I hope I said those numbers right. 762, my apologies. Actually, it should be minus 772. So my apologies that my thing is wrong here. So when I get that, the difference here should be 23. Okay, so not bad. So there's my 23. So it's energy releasing, but here's that whole correction. It ends up, the OH bond of water is actually 498, not 467. So I actually am going to subtract even more in this spot right here. So that's a whole difference of 31. So that 31 difference means it's going to be around 54. So hopefully this seems better. So I got my math correct in the next go around. So hopefully this seems okay, just number crunching. So the reality is this table is only as good as the bonds that we use in it, how close the generic bond is to a specific bond. So it's not the perfect method, but at least gives us a general idea in the ballpark. So either way, negative 23 or negative 54 still meant it was energy releasing because entropy is roughly 1 or 0, I mean, breaks even. That means delta G is roughly equal to delta H. Okay. So transitioning, so that's the end of thermo. Thermo ties into kinetics. So again, thermo tells me how much energy was involved, either absorbed or released. Kinetics tells me how fast a reaction goes. And this has to do with temperature of the system, but also rate at which the product can be formed from reactants coming together. So let's just start with a simple Beers plot where we look at absorbance over wavelength for some system, and we find that there's an absorbance, let's say 312, something like that. So UV absorbance for one of the compounds in solution, and then some broad roll, maybe around 600-ish, 550, 600. Okay, as I study this reaction, that's at time 0. I mix the two together, the reactant and product, and this first peak goes down. If it's going down, chances are it's probably a reactant, but I don't know for sure yet. This one is probably a product because it's growing in. This is probably a reactant because it's going down. This is probably a product because it's starting to grow in. The reason I have question marks is because it can't always necessarily be a reactant. It can also be potentially a catalyst that got consumed and then it eventually will get regenerated, or it could be an intermediate product that's forming. I mean, there's different things that can happen here. Okay, it isn't until I do this third trial. This continues to go down, so definitely it's a reactant. This one continues to go up, so it's definitely a product. But what happens now is this catalyst, it was there in the beginning, then it diminished to hardly anything, and then it started to grow back in. The intermediate wasn't there in the beginning, but it appears and it stays high for a while, but then it starts to disappear. Depending on how this intermediate stays, they sometimes refer to this as a steady state, meaning if it stays constant, then it is being formed as fast as being consumed. So the substrate or the reactant is going on to the catalyst and holding there until it can be released. And so if you have so much reactant in the solution and so little catalyst, and the catalyst will get saturated, and it'll have the steady state. It can only go as fast as the catalyst can turn that substrate or reactant over into product. Okay, so feeling pretty confident about what these are. So there's my 4 experiments. That's not as important as the trend. So the concentration of the reactant over time, I'm going to note that it goes down. So let's say we did this for reactant. We're going to see it drops readily at first, but then drops less and less and less with time because it depends on its concentration. So reactant is going to go like this, and eventually when it goes flat, it's reached some sort of equilibrium. Products, on the other hand, grow in. So they start at 0 and they level off. So products can grow in and level off, a reactant is going to drop and level off. Notice it's not dropping to 0 because there is always some available at equilibrium because there's always a dynamic equilibrium. Reactants go forward as quickly as products go back. The other ones that are interesting, the concentration of the catalyst is there in the beginning, then it gets turned into an intermediate. If you're taking biochem or you're going to take biochem, you'll know that the enzyme gets turned into enzyme substrate complex, an intermediate, and then once it runs out of substrate, once you run out of reactant, the catalyst gets regenerated. So catalysts are there in the beginning, they're consumed in the middle of the reaction, but then they're regenerated at the end. And then finally, then the intermediate grows in, stays steady for a while, and it's the steady state approximation. And then when I start running out of reactant, it dies off pretty quickly. So these 2 graphs probably look familiar. These 2 may be a little bit different, but need to hang on to those thoughts. For OChem, I'm probably going to only consider this diagram and maybe look at this one. Okay, so the rate of a reaction defined as the rate at which the product is formed or the rate at which the reactant is consumed. In theory, they're one and the same, but if you have 2 reactants combining to go to 1 product, then there's a factor of 1/2. Or if you have 2 products formed for every 1 reactant, there's a factor of 2. So it all has to do with what the number situation is within the balance equation. So there might be a factor of 1/2 or a 2, a third or a 3, depending on how you look at it. Okay, last of the things we want to look at until for this video, we'll add one more. As the reaction heats up, the number of molecules at a low temperature is so many, but if I heat up the reaction, heat up the system, heat up whatever the container is, the average molecule is going to start going faster. So they all sort of shift to higher energy. So I have fewer molecules at low energy and more molecules at high energy. So lower temp is this one, higher temp is this one. And there is something called the activation energy, the energy needed to initiate some sort of chemical reaction, and then it'll carry itself on once you form that transition state. But let's say that activation energy is right on here. Notice the cold temperature only has a certain amount can make it, but the hot temperature has much more. So in other words, let's say there's my activation energy. This is a very small space for the cold, but there are far more molecules that have enough energy when it's hot. So there are the number of molecules that can do it when the temperature is hot, as opposed to here, the ones that can do it when it's cold. So the rate of a reaction can go up as you either A, raise the temperature so more molecules can overcome the barrier, or B, lower the activation energy. So this ratio is even more pronounced. So that covers what we're going to do for this. So I tied off thermodynamics, started into kinetics. We're going to look at reaction order and things that are a little more important in terms of OChem. So thank you for joining. Have an absolutely wonderful time, and I hope to be able to stop this video soon. There we go. So I will see you soon. Bye.